Good morning, I'm Manuel Zarzo, and here today in Unit 6, Inference into Normal Populations, I will talk about the comparison of variances and means. And I will work with the following example. Imagine that we have two computer programs that we will call A and B, which are available to search different files in a hard disk. So we have like two populations studied, which will be the files in the hard disk that can be searched by programs A or B. So the random variable that we have measured is the time required to search a file, okay? And then we assume that the variable is normally distributed. Okay, this is important because in statistics, the formula that we apply assume normality, as you know. Okay, so we have these two populations. Both are normal. One has an average of M1 and standard deviation sigma 1. The second has an average M2 and the standard deviation sigma 2. Then we make a sample. We take a sample from the first and a sample from the second. In both cases, the sample is from 10 values. So the statistical parameters that are computed from both samples is the average and the standard deviation. Okay, so we compute the sample mean, the sample standard deviation. So we want to check the hypothesis if M1 can be considered equal to M2 and the hypothesis, or different, sorry, and we want to check the test if sigma 1 can be considered equal to sigma 2 or not. Well, so we will start with this second case, comparison of variances. Good. So this is the null hypothesis that both populations have the same variance versus the alternative that the variances are different. Okay? Well, if the null hypothesis is true, both will be similar, and the ratio S1 squared divided by S2 squared will be similar to 1. Okay? The null hypothesis will be rejected if this ratio is much bigger than 1 and cannot be rejected if it is more or less around 1. But what should be considered as being similar or not? So we need some kind of statistical distribution, and it is based on the Fisher's distribution. So if the null hypothesis is true, we know that this ratio of sample variances follows a Fisher's distribution, being the degrees of freedom n1 minus 1 in the numerator and n2 minus 1 in the denominator. So the steps for this comparison would be the following. So these steps are when when we use the the Fisher's table, because because the real values are on the right side. Okay, so this is why we divide the highest by the lowest. So we have two samples. We divide the highest by the lowest. Okay, and then the test is if we compare it with the critical value from the distribution, from the Fisher's distribution, with n1 minus 1 degree of freedom in the numerator and n2 minus 2 in the denominator. Okay, there's an alternative procedure, which would be to obtain a confidence interval for the ratio of population variances. The formula is included in your math tables, so this will be another procedure. So if the value 1 is outside this interval, we will say that we will reject the null hypothesis, but if the value 1 is inside this interval, we cannot reject the null hypothesis. So now we will apply these formulas based on an example. So imagine, as I was saying, that we have two computer programs that can be used to search files in a hard disk. So in order to determine which one works faster, so we take a sample of 10 files which are searched by each program, and then we measure the time required to find each file. So the object would be to compare two populations, files searched by one program and files searched by another program. And then we have a sample of 10 files with program A, 10 files with program B. Okay, the value measured experimentally is the time to find the file, and then imagine that these are the results. So 10 values from the first population, 10 values from the second population, okay, and then we obtain the sample mean, we obtain the sample standard deviation. Well, good. So if the null hypothesis is true, okay, then we know from the theory that the ratio of sample variances will follow a Fisher's distribution. Okay, so in this case, the degrees of freedom is 9 and 9, because the sample size was 10 in both cases. So we go to the Fisher's table with alpha 5%, and then we will read that the critical value is 3.18. Okay, this is the critical value with an alpha 5%. So we compute this formula. We take the highest value of the sample variance divided by the other value, and then this is 1.14, which is here, obtained value. And then this is in the region of frequent values. Okay, as this is a frequent value, we don't have enough evidence to reject the null hypothesis. Okay, so the null hypothesis cannot be rejected. The conclusion would be that there is not enough evidence to affirm that the variance of program A or B is different. Okay, so what happens if the conclusion would be which is different? So, I mean, usually we have the test for the comparison of mean and then the test for comparison of variances. So usually the comparison of variances is carried out first because in the test of comparison of means we assume equal variances. Okay, so what would happen if this hypothesis is rejected? Well, the subsequent test for the comparison of mean would be just approximate, but anyway, it is quite robust, okay, because it means that although this is not mathematically exact, more or less we can rely on the results that we obtain. So this is why usually we first compare the variances and next we make the comparison of the means. Okay, so analysis with stack graphics. We have to use the option compare to samples, independent samples. Then we will say that the ratio of variances, the same value that we have computed, although the software computes the confidence interval for the ratio of population variances. As I was explaining, as the value 1 is inside this interval, the conclusion is do not reject. So there's another method, the F test, so the null hypothesis, sigma 1 equals sigma 2. Remember that sigma means the Greek letter, which is used for the population standard deviation. So both populations have the same standard deviation. Okay, alternative hypothesis is that they are not equal. So the contrast statistic is the ratio. So this ratio is the contrast statistic, and the software computes a p-value. Remember, as I explained in the previous video, that always we have to compare the p-value with alpha. So always that the p-value is bigger than alpha, we cannot reject, and always that the p-value is less than alpha, we can reject the null hypothesis. Okay, then now I will explain the comparison of means. So this is the null hypothesis, the mean are equal versus the alternative that the mean are different. So if the null hypothesis is true, we'll have that the sample mean of the first will be similar to the sample mean to the second population, and then their difference will be small, will be around 0. So we have this formula. Okay, so we have this formula. Then if we this formula assumes that the variances are equal. This is what I was explaining before. This is why usually we carry out this test before the test for the comparison of means. But remember, if the conclusion is that they're different, anyway, this formula can be useful and we can obtain a useful interval because it is quite robust. So assuming that the null hypothesis is true, then this difference will be 0, and this is simplified. So the difference of sample means divided by a certain standard deviation, a global standard deviation, follows a student t-distribution with degrees of freedom n1 plus n2 minus 2. Okay, so what is this kind of global standard deviation? Well, the formula is a bit long, but it's this one. Okay, it's based on n1, n2, s1 squared, and s2 squared. Okay, a bit more complex formula, but you can apply mathematically. So if both sample sizes are equal, so the formula is simplified just like that. So that's it. In this test, the same test can be solved with ANOVA, with analysis of variance. Okay, ANOVA can allow the comparison of means for two populations or more than two populations. But if we have just two populations, we also can carry out the same comparison with ANOVA. Okay, so in this case, we have this is the difference of means, this is 0.74. So we compute this global standard deviation, and then we compute the t calculated. Okay, and then the critical value for 18 degrees of freedom is a value 2.1. Okay, so we have the region of frequent values inside and the region of not frequent values in the right tail and in the left tail. So in this case, we obtained a value 1.39, the value obtained with the t calculated, which is inside the range of frequent values. It means that we cannot reject the null hypothesis. Okay, do not reject would be the solution. So results are consistent with the hypothesis that both populations have the same mean, or we can say that we don't have enough evidence to say that the population mean is different. Okay, so also based on the formulas of the previous slide, we can obtain a confidence interval for the difference of m1 minus m2. Okay, this would be like an alternative way, but more informative, to analyze the results from this comparison. Okay, m1 minus m2 belongs with a high probability to this interval. Okay, this is the same formula that I explained in the previous slides. Okay, this example would be minus 0.37 until 1.85. In this particular case, we have to check that the value 0 is inside. So as the value 0 is inside, okay, we can say that 0 belongs to this interval, and so m1 minus m2 can be assumed as 0. It means that m1 equal m2. So as the value 0 is inside, we cannot reject this null hypothesis. So this is an equivalent way to solve this hypothesis test. So the answer would be that we can affirm with a confidence of 95% that the difference m1 minus m2 is comprised between minus 0.37 and 1.85. Analysis with star graphics. Okay, this would be for the comparison of means. Okay, look that it says assuming equal variances. Okay, this is the most frequent case. Then a t-test, assuming the null hypothesis, the mean 1 equal to the mean 2, versus the alternative that they are different. And assuming equal variances, it leads to a computed t-statistic. Okay, the p-value is 0.18, and then once again, and as alpha 5% is the most frequent value, as this p-value is bigger than 0.05, the conclusion is do not reject the null hypothesis. Okay, the option is this: compare two samples, independent samples. And then this is what I have explained here in this video about comparison of variances and means.